Okay, more transformations. This time we're going to look at this function e to the x a little bit more closely. Again, it has a lot of applications, so being a little bit more familiar with it is going to be helpful to us as we work with it. Pause your video and make yourself a little graph here in the first box. I'm actually not going to graph the last two, so don't worry about those. But we need to have the graph here, and I apologize, it's not already there. Okay, so you should have your graph drawn. We're going to draw the basic graph of e to the x again. Okay, e is just a number. So we need to be able to plot that out. First of all, again, I'm just doing plain old e to the x, not the transformation yet. So if I have e to the 0, no matter what the base is, anything to the 0 is always going to come out to be 1. Okay, e to the first, we saw on our calculator, e is about 2.718. Okay. And then finding e squared, I don't have that in my head, so let's go ahead and figure that out on our calculator. Good chance to practice it. This button above the ln, so I know I'm going to put an exponent, I might as well use that e. E to the power 2, 7.4 as we plot that out. Okay, I have 1, 2, 3, 4, 5. We'll put a 7.4 there for 2. So then we have the negatives. Okay, let's find our value for e to the negative 1. Okay, 0.36. And e to the negative 2, we can really make a prediction. It's going to be just a bit smaller. And we're going to get closer and closer to that x-axis again. So we have this value. We have our graph of our e to the x that looks like this. That's our basic exponential function for e to the x. It doesn't look a lot different from our one with 3 to the x because e is 2.7. So it's very close to 3. So it looks very similar to our function for 3 to the x that we have above. Now we want to do our transformations. I really wanted to look at this transformation because I want you to see a horizontal translation again. So notice it's applied to x. It's multiplying the x. We have a horizontal translation. Everything horizontal happens in reverse. So this time we have a horizontal shrink. And since we're multiplying by 3, we're shrinking by 1/3. Okay, anything horizontal is in that reverse. So horizontally shrinking by 1/3. That means we would take every x value and multiply it by 1/3. So here, if I'm at 0, if I multiply 0 by 1/3, it remains the same. This x value of 1, if I multiply it by 1/3, becomes 1/3. So I end up moving towards the x-axis to an x value of 1/3. This point had an x value of 2. I multiply that by 1/3, I get to 2/3. Okay, over on the left of the x-axis, so they're negatives. If I have negative 1, I multiply that by 1/3, I get negative 1/3. Okay, if I have my x value at negative 2, I multiply that by 1/3, it's negative 2/3. And we get this really tight curve that's close to the axis. There's our horizontal shrink. It's like I've shrunk it towards the y-axis. Okay, I really wanted to look at that one again because I know that's caused some trouble. Let's just write out the translations for these other two. So we have e to the negative x. It's applied to the x, so that's a horizontal change. Negative is a reflection, so horizontal reflection, sideways over that y-axis. So we have a reflection over the y-axis. Okay, and here we have 2 times e to the x. Multiplied to the whole e to the x function, so it's applied to the whole function, so it's vertical. We have a vertical stretch by 2. Okay, not much different than what we saw when we did our translations with 3 to the x. All right, let's continue on. Exponential functions are practical in many ways, but they aren't entirely the whole story. A lot of functions do not continue to grow, or a lot of scenarios that grow exponentially do not continue to grow forever. we have another function that gives us a better picture of a lot of growth, especially population growth. Population growth can grow exponentially, often at the beginning when, if we think about how some of the suburbs grew that are further out, they kind of had a boom. They had this big growth time. But then because of space, we can't have it grow forever. There's not room for more houses. So it starts to slow down. Okay, that works for bacterial growth. If you have a petri dish, you have this exponential growth for a period of time. But then it starts to slow down as all the nutrients that are in that petri dish are being used up. Okay, things start to slow down and they don't continue to grow exponentially forever. And so what we have are these logistic functions. They have the exponential curve as part of it, but then they show this slowing down at the end. Okay, in general, exponential functions are continuous. There is no domain restriction. If our variable is in the exponent, I can have exponents that are 0, I can have exponents that are negative, we can have exponents that are positive. There's no undefined values. So our exponential functions are continuous. An exponential function increases at an ever-increasing rate. It keeps getting bigger and bigger and the larger changes over time. It is not bounded above. But again, this is not realistic. In many growth situations, there's a limit to the possible growth. And so that's where we have these logistic functions. They are kind of a lot of values put together. But here's our basic logistic function. Again, here's the same function in an E form because a lot of times E is an appropriate value for an actual population growth. Okay, there's some key things that are in this logistic function. And one is to understand that this C, the numerator there, is the limit to growth. Okay, similar, all the rest of it's pretty similar. B has to be a base, but this time B is going to be something less than 1. Okay, everything else is a positive constant. So here we have our logistic growth functions. So here, let's just take a look at the function itself before we look at it in application. We want to find our asymptotes. We want to find the y-intercept for this particular logistic growth function. So here we have it in the E form. When we have this, let's just take a look at it in our calculator for a moment so we can actually see what's going on and see what this curve looks like. We have 15 divided by, and if you want to put in with your alpha y equals and put in the big fraction, that's fine. Otherwise, put the whole denominator in parentheses, 1 plus 3 times e to the negative 2x. Okay, if we take a look at the graph of that, so I have a feeling it's in a weird window. Just go to your standard window. We can start to see part of it. We won't be able to see all of it. Okay, we see this growth looks like our exponential function. It's curving upwards. Okay, but if you start to notice, it's not quite curving as sharply as the other ones did when we had our exponential functions. And we see that our C, our limit to growth, is 15, which means the most that it can grow to is 15. So when we set up our window, we actually want to go up as high enough to see 15. I'm going to go ahead and see 20 so we can get a better view for it. Well, it doesn't work if you change your X. We want to change our Y. So I'm going to go back to 10 there. I want to go higher up to 20. There we go. Okay, see that? It slowed down. It started to almost come to a stop for its growth. It had the exponential curve here, but then it decreases and stops continuing to have that exponential curve upwards, and it starts to slow down. Okay, we see two asymptotes. We see an asymptote at y equals 0, just like our exponential functions. And then we see a second one up here at y equals 15. So for our for this logistic growth function, we have two horizontal asymptotes. We have y equals 0 and y equals 15. We then have our y-intercept, a key value on our, really any function, but in particular our logistic growth functions. What happens at time 0? Okay, well, let's put 0 into our function. We want to find g of 0. So it's 15 over 1 plus 3 times e to the negative 2 times 0. Okay, well, e to the anything, e to the 0, or anything to the 0, I should say, is 1. So we have 15 over 1 plus 3 times 1, or 15 over 4. Okay, so our y-intercept is 0. And if I'm going to plot this, that's 3 3/4. Might be another way, nicer way to plot that. Okay, to draw our graph, I'm going to set up our axes. Again, nothing's going on below the x-axis, so let's keep that down there. We need to get all the way up to 15. I'm going to count by 3s. On the x-axis, I'll keep counting by 1s, no change in that. We see our 2 horizontal asymptotes, one up at y equals 15, and one down at y equals 0. Oh boy. Sorry about that. Let's go ahead and pause it and go ahead and you can copy that down. I did count by 3s to plot this out. And I have my 2 horizontal asymptotes at y equals 0 and y equals 15. Okay, pause it if you need more time to get that drawn in. All right, so then I want to plot this y-intercept. 0 and 3 3/4. So that's about here. And I'm not looking for perfect shapes to these graphs. A good sketch simply shows that it comes along the x-axis. Maybe this in blue. So we come along the x-axis here. We go through our horizontal asymptote, it curves, and then it starts to slow down the curve, and it goes along our second horizontal asymptote. Okay, here is the basic shape to our logistic function. Obviously, you can use your calculator and plot out some exact points to help you get a better shape to this, but this is enough. This gives our curve and draws out our exponential function well. Okay, I'm going to pause this, and we're going to have one last video to finish these notes up.